Okay, let's dig into this. We've all heard those stories, probably since we were kids, right?
Hmm.
You know, the dogs howling right before an earthquake or birds suddenly vanishing from the coast just hours before a tsunami.
Yeah, that whole idea.
It's this really old, kind of captivating idea of the living sensor that animals just know when a disaster is coming way before we do.
It's fascinating how long this idea has persisted.
Hmm.
It's not just, random folklore. It's documented way back.
Mm.
The earliest clear record, 373 BC, Greece.
Wow, that far back.
Yeah. Apparently, days before this really devastating earthquake hit, people reported seeing rats, weasels, snakes, even centipedes just packing up and leaving the city, fleeing for safety.
That's incredible. A specific animal exodus noted more than 2,000 years ago. So, okay, our mission for this deep dive is really to get past those compelling anecdotes.
Yeah.
We want to figure out, is this instinct, this supposed ancient warning system, something that modern science can actually verify? Can animals truly predict disasters? We're looking at this through two lenses: hard science, animal physiology, and also traditional knowledge systems.
And when we talk prediction, we really have to split the timeline almost immediately. There's the, let's say, easily verifiable part, the immediate warning, just seconds before something happens.
Okay.
And then there's the much tougher question, prediction days or even weeks in advance.
Right, let's start with the immediate one, earthquakes. That seems tied pretty closely to the actual physics of the event.
Precisely. So an earthquake releases two main kinds of waves. First, there's the P wave, the primary wave. It's faster, smaller, kind of a subtle compression. We humans, we usually don't even feel it.
Okay.
But right behind it comes the S wave, the shearing wave. That's the bigger, slower one that causes most of the shaking, the damage.
Ah, so the key is the gap between them.
Exactly. Animals with really keen senses, especially those tuned into vibrations,
Yeah.
they could detect that subtle P wave, maybe seconds before the destructive S wave arrives.
That makes so much sense. So the animal isn't predicting the quake in some mystical way. They're just reacting to the first physical sign of it hitting.
That's the idea. And from an evolutionary perspective, it fits perfectly.
How so?
Well, one source called it exaptation. Evolution didn't need to invent some brand new earthquake sense.
Right.
It probably just repurposed an existing instinct.
Mhm.
Think about the escape response you'd need to feel a predator's heavy footsteps, or maybe the vibrations from an approaching fire. That sensitivity to vibration just got adapted for a new role.
It's not magic, it's just biology finding a new use for an old tool. Clever.
And it's deeply ingrained. This ability to detect low-frequency seismic signals. It likely evolved way, way back. We're talking before the mid-Ordovician period in vertebrates.
It's ancient stuff.
Very ancient. Which explains why we see this kind of escape behavior across so many different kinds of animals. Fish, mammals, you name it. It's a built-in threat avoidance system.
Okay, so the immediate reaction. Explainable. Physics, biology. Got it. But now, the real head scratcher. Predicting things days or weeks out.
Ah, yes, the big mystery.
That means they'd have to be sensing some kind of precursor, right? Something physical or chemical that we humans are totally oblivious to, or at least aren't measuring reliably yet.
And this is exactly where the scientific skepticism really kicks in. Because, look, the anecdotal evidence is overwhelming. Everyone has a story. But the hard data, it's often, well, flawed.
Flawed how?
Take the 2018 analysis from the GFZ German Research Center. Big study. They pulled together 180 studies covering almost 730 reports across 130 species, dogs, cows, even silkworms.
Wow, 700 plus reports. That sounds like pretty strong evidence on the surface.
It sounds like a lot, yeah. But here's the catch. They found that almost all of them, all but 14 reports, were based on just a single observation.
Ah, so no long-term baseline.
Exactly. No continuous data showing what the animal's normal behavior is day in, day out, without that baseline.
You fall right into confirmation bias.
Right.
Like, my dog acts weird maybe 100 times a year for no reason I can see, but if one of those times happens to be right before an earthquake?
Bingo. That's the one you remember. You impose a pattern after the fact because it fits the narrative you're looking for.
Yeah.
It's a huge challenge for rigorous statistics in this area.
Yeah, I could see that.
Think about this other study from 1988, published in California Geology. They tried to find a statistical link, kind of creatively. They looked at the number of lost pet ads in the San Jose Mercury News.
Lost pet ads. Seriously?
Yep. And they tried to cross-reference the dates of those ads with earthquake dates in the San Francisco Bay Area.
Yeah.
The idea being maybe pets panic and run away beforehand.
Huh. Okay, kind of a weird metric, but I guess I see the logic. Did it work?
Nope. Found no correlation at all. Even with that proxy, nothing solid. So the scientific conclusion generally remains. If long-term prediction is happening, the animals must be sensing real physical or chemical changes before the main event.
Like what? What kind of changes?
Things like tiny tilts in the ground, maybe changes in groundwater chemistry or humidity, or
Hmm.
possibly subtle variations in electrical or magnetic fields. Things we aren't typically monitoring everywhere all the time.
Okay, this is where it gets really fascinating for me because when you start looking at animal physiology, it stops feeling like some vague sixth sense and starts looking like, well, like they just have superior biological hardware.
Extremely sensitive hardware.
Take smell, olfaction.
Right. Our sense of smell. It's almost rudimentary compared to a dog's. We might have, what, 6 million olfactory sensors?
Something like that.
A typical dog can have up to 300 million.
300 million, that's staggering. Our noses are practically useless in comparison.
It's why people say dogs can almost smell time itself. That incredible sensitivity basically lets them act like biological gas detectors.
Yeah.
The theory goes that as tectonic stress builds up deep underground before a quake, it literally squeezes gases or chemicals out of the rocks. Things we wouldn't notice, maybe toxic stuff like radon, sulfur compounds, perhaps carbon monoxide.
And is there any proof of that gas release happening?
There's some suggestive data. Before that big 7.7 magnitude quake in Gujarat, India, back in 2001, satellites actually detected this huge area, like 9 square miles, with unusually high carbon monoxide levels.
Whoa.
The thinking was this gas was being forced out of the rocks by the immense pressure building up.
So the dogs aren't necessarily sensing the earthquake itself weeks in advance, but maybe they're sensing this toxic change in the air quality. Their anxiety running away, it's a totally logical response to a suddenly poisonous environment.
It's a plausible mechanism. And it fits with what else we know dogs can smell, right? They can detect tiny chemical changes associated with illnesses like cancer or diabetes, even pregnancy seizures. They're smelling unique, minute chemical signatures.
Amazing. Okay, what about other senses?
Then there's magnetoreception, the ability to sense magnetic fields. This got really interesting with the discovery of these tiny, perfect crystals of magnetite.
Magnetite, like lodestone.
Exactly, a magnetic iron oxide. They found these crystals inside organisms ranging from bacteria all the way up to honeybees, pigeons, fish. They seem to act as tiny biological magnetic receptors, like built-in compasses.
And some animals have really, really refined this sense.
Oh, absolutely. Honeybees are a prime example. They've apparently pushed their magnetic sensitivity almost down to the thermal noise limit. Basically, they're about as sensitive as physics allows.
Wow.
Their system is tuned specifically to really ultra-low frequencies, below 10 hertz, and their sensitivity is down the low nanotesla range.
Nanotesla. Okay, break that down. How sensitive is that? Give me some context.
Okay, think about a fridge magnet. That generates a field in the millions of nanoteslas. The Earth's background magnetic field is around 50,000 nanoteslas. We're talking about animals potentially detecting changes measured in single digits of nanoteslas. Tiny fluctuations.
Single digits. That's almost nothing.
Almost nothing to us. But get this. The magnetic anomaly recorded just before the 1989 Loma Prieta earthquake. It peaked at just over 6 nanoteslas.
6 NT. So, well within the detection range you just mentioned for honeybees.
Exactly.
Huh.
Suddenly, it's not a supernatural sixth sense. It's highly advanced biological detection hardware tuned to pick up measurable physical precursor signals that we're just starting to understand might exist.
That completely reframes the conversation.
It really does.
So far, we've been pretty focused on, earthquakes and isolating these specific animal senses in scientific studies. But what happens if we shift focus? Look at sustained multi-generational observation. That brings us to traditional knowledge, especially in places really vulnerable to climate shifts like the Pacific Islands.
Yes. Traditional knowledge, or TK, particularly in the Pacific, is so much more than just all the stories. It's this deep, accumulated, place-based understanding. It's actively used to anticipate and respond to climate changes, both short-term and long-term.
It's a survival system.
Absolutely. Our sources really emphasize this. Pacific Islanders survived for millennia, facing huge environmental threats. That wasn't luck. It was by design. Their knowledge is their resilience strategy.
And their animal indicators, what the source is called Tier 1 TK, are fascinating because they often relate to weather, right? Like tropical cyclones, which happen much more often than big earthquakes.
Exactly. A classic example comes from Tonga and Fiji. It
Yeah.
involves the frigate bird, the Lophotalamatangi. It's an ocean bird, normally stays out at sea.
Right.
But if people see these frigate birds flying inland, across the land, sometimes even skimming rooftops,
Mm.
that's taken as a reliable sign that a tropical cyclone is on its way.
And that actually lines up with modern science, doesn't it? Something about infrasound.
It does, perfectly. Scientific studies confirm that birds, especially big seabirds, can detect infrasound. These are really low-frequency sound waves, below 20 hertz, too low for us to hear. Massive storms generate these waves over long distances.
So the birds are hearing the storm coming acoustically from far away and flying inland to escape it.
That's the thinking. TK observed the behavior. Science eventually explained the mechanism. It's a great example of convergence.
What about insects? You mentioned silkworms earlier, but TK uses others too.
Yeah, in the Solomon Islands and Fiji, they pay close attention to hymenopterids, that's bees and wasps. If these insects are seen building their nests or hives unusually close to the ground instead of high up in trees or under eaves,
Hmm.
that's interpreted as a prediction, not for tomorrow, but for an unusually wet season or a cyclone maybe 3 or 4 months down the line. It suggests they're anticipating high water levels or strong winds that could destroy higher nests.
Months in advance. That's incredible foresight. And it even extends to plants. Plants aren't exactly running away.
Right. But Tier 1 TK absolutely includes plant observation. Things like seeing anomalously heavy or early fruiting. For instance, breadfruit growing in massive bunches, like more than 3 fruits on one branch, when that's unusual.
Yep.
Or if a plantain's central shoot looks really curled instead of growing straight, these are seen as signals from the plants, possibly maximizing their reproduction before a period of stress like a cyclone or very heavy rains.
Fascinating. And then there are atmospheric signs, things that were probably noted for centuries but now have scientific explanations.
Definitely, like the lunar halo, seeing the moon with a ring around it. That's a classic, very old sign predicting imminent rain or storms.
And science confirms that.
Yeah, that halo is caused by light refracting through ice crystals high up in cirrus clouds. And those types of clouds very often precede incoming storm systems. So the observation was spot on.
And observing distant ocean waves, too, not the ones breaking on shore.
Right. Changes in the shape or the pattern of how waves are breaking way out on the horizon.
Yeah.
Experienced observers say this can predict a cyclone maybe even a month before it actually hits.
How?
Because big, distant storms generate these long, rolling swells called long fetch swells. These waves actually travel much faster than the storm system itself, so they arrive first, like an early signature of a major event coming over the horizon.
The real power of TK, though, seems to be that it doesn't just stop at prediction. It flows right into practical action, resilience.
Tier 2 TK, right. How to survive.
That's arguably the most crucial part. It's not just knowing, it's doing. The coping strategies that allow communities to survive by design, not just by chance. This covers everything from food security,
Like what?
like developing specific crops that are more resistant to drought or salt spray, or techniques for bulk storing food, like fermenting root crops like cassava or taro, so they can last for months after a disaster wipes out fresh food sources.
Smart. And the architecture, the traditional buildings are incredible. Oh, absolutely. Traditional cyclone houses are engineering marvels. Think of the Gamali in Vanuatu or the Samoan fail, which
Mhm.
often doesn't even have fixed walls. They're specifically designed to withstand hurricane-force winds.
How do they do it?
They use flexible materials lashed together with rope or vines, not rigid nails. This allows the structure to bend and give under pressure rather than snapping. And they often have low, rounded profiles to help the wind flow over them, reducing resistance.
Flexibility again, it seems to be a core principle. Adapt, bend, don't just rigidly resist.
Exactly. And that adaptability even extends to where people built. In places like Yap, they traditionally built houses on raised stone platforms called wanbi
Yeah.
to mitigate flooding and storm surges. And get this, it was an adaptive strategy over time. If sea levels rose or flooding got worse, they could incrementally raise the height of that platform over generations. Built-in adaptation.
That's amazing. This blend of deep observation, biological insight, and practical adaptation.
Hmm.
It brings us kind of full circle back to the present day and attempts to bridge this ancient wisdom with cutting-edge tech, like that Max Planck Institute project.
Right, the collaboration between the Max Planck Institute of Animal Behavior and Tractive, the pet GPS tracker company.
What a doing!
What's really game-changing here is the scale. They're using real-time activity data from nearly 1 million pets, mostly dogs and cats, wearing these GPS trackers all over the world.
1 million pets. Wow.
And the trackers use this sophisticated algorithm, VDBA, Vectorial Dynamic Body Acceleration. It basically learns the precise, normal, everyday activity baseline for each individual animal. What does a specific dog usually do at 3 p.m. on a Tuesday?
So they get a fingerprint of normal behavior for each pet.
Exactly. Then the goal is to use AI to constantly scan this massive data set. They're looking for sudden, synchronized, highly unusual spikes in activity across hundreds of pets in the same geographic location at the same time.
So instead of relying on one person noticing their single dog acting weird.
They're looking for a statistically significant anomaly across a large population in one area.
Yeah.
If suddenly hundreds of dogs in, say, a 50-mile radius simultaneously start pacing, trying to flee, or showing stress behavior that's way off their normal VDBA baseline.
That could be a verifiable real-time signal. It takes it out of the realm of anecdote.
Potentially, yes. It's an attempt to build a high-tech early warning system by essentially digitizing and scaling up what traditional observers have been doing for centuries. It bridges that gap between anecdotal reports and hard, quantifiable data.
It's the ultimate mashup, isn't it? Using these hyper-tuned animal senses that evolved millions of years ago, but capturing and analyzing the data with modern AI to maybe recreate that ancient warning system.
It really highlights how valuable different kinds of knowledge can be.
This whole deep dive has been really eye-opening. We've kind of walked down two parallel paths. On one side, the incredible, super sensitive biology of animals, magnetic senses, smell, hearing things we can't. And on the other, these ancient, practical, deeply embedded traditional knowledge systems built over millennia specifically to survive existential environmental threats.
And perhaps the most provocative thought to leave you with is this. Maybe the ultimate key to navigating future disasters, especially with climate change, isn't solely about building more sophisticated satellites or seismic sensors, although those are important.
Okay.
Maybe true resilience lies in learning how to respectfully combine that deep, place-based, traditional knowledge proven to work over centuries, with the verification and scalability that modern science and data can offer. How much vital, life-saving insight, currently dismissed because it's just an anecdote or because we don't yet have the perfect instrument to measure its physical basis, are we overlooking? Recognizing the value in that evolved resilience might be central to our own survival.